Okay, so welcome back for round 3. Yesterday, the kind of takeaway message that we learned was that Twistor theory generates solutions to linear massless free field equations, or the zero rest mass equations, on complexified Minkowski space. And the kind of one-line statement of this was this theorem that we wrote on the board that there's a kind of one-to-one correspondence between helicity H zero rest mass fields on complexified Minkowski space and cohomology classes on Twistor space that are homogeneous of a certain weight. So today, we're going to talk about how Twistor theory can solve some nonlinear equations. Not just any nonlinear equations, but in particular the self-duality equations in the context of non-abelian gauge theory. So let's start by talking about self-dual Yang-Mills fields, or gauge fields. So yesterday, we wrote a bunch of two-spinner decompositions of Maxwell fields on the board. All of that is basically going to go through unchanged today. You just have to imagine that there's a Lie algebra index hanging off of everything. So let's let A alpha alpha dot be a connection one form taking values in the Lie algebra, let's say G of some gauge group big G. The field strength of the associated connection, which I'll call big D alpha alpha dot, and locally we can write this as little d alpha alpha dot plus A alpha dot. This is F alpha alpha dot beta beta dot, and it's just given by the bit we wrote down yesterday for Maxwell fields plus a commutator term coming from the non-abelian structure of the gauge group. So this bracket is just the Lie bracket on the Lie algebra little g. And non-abelian gauge transformations these are given by matrix valued functions. Let me call them, say, little h of x, such that, so our gauge transformation is given by sending the gauge potential A alpha alpha dot to H inverse D alpha alpha dot H plus H inverse A alpha alpha dot H, under which this field strength transforms covariantly. So F alpha alpha dot beta beta dot goes to H inverse F alpha dot beta beta dot H. Probably many of you have seen and worked through these sorts of things before. This is more just a standardized notation. Sometimes there are I's that float around here or different signs. These are the conventions that I'm going to be using. OK, so just like in the abelian case yesterday, exciting. So just like in the abelian case yesterday, we can decompose the field strength into two spinor irreducibles because we know that it's skew symmetric under interchange of the 4 vector indices, if you like, F, A, B. So just like the case of Maxwell fields that we discussed yesterday, we can decompose F alpha alpha dot beta beta dot into an epsilon alpha beta F twiddle alpha dot beta dot plus epsilon alpha dot beta dot F alpha beta, where this guy is the self-dual and this guy is the anti-self-dual parts of the field strength. Okay, so that decomposition happens in exactly the same way as before. The only thing to keep in mind is that these the F twiddle and the F are Lie algebra valued, so they're valued in the adjoint of the gauge group. And they're not just given by one derivative on one A. There's also some bit of this commutator, which bit corresponds to which spinor index you contract on to define F twiddle or F. Man, I think this is going to stay on. All right. Is the mic still picking me up there? OK, that's good enough. All right, so, right. So just as in the abelian case, the fact that F arises as the field strength of a connection means that it automatically satisfies a Bianchi identity. So which is just written in terms of the spinor decomposition. It's just d beta alpha dot F twiddle alpha dot beta dot minus d alpha beta dot F alpha beta is equal to 0. So we get that for free. That's not a dynamical equation. Then the Yang-Mills equation for F is d beta alpha dot F twiddle alpha dot beta dot plus d alpha beta dot F alpha beta equals 0. So what we observe straight away is exactly what we observed yesterday. If you set the anti-self-dual part of the gauge field to 0, so if F alpha beta is equal to 0, then you automatically solve the Yang-Mills equations. Because in this self-dual sector, the Yang-Mills equation is just equivalent to the Bianchi identity. Okay, so this is just a kind of nonlinear version of what we said about Maxwell theory yesterday. Okay? Now yesterday, when we made this observation, it was sort of in the service of saying that, well, self-dual Maxwell fields are just helicity 1 zero rest mass fields. So they're an example of these linearized equations that we get to solve using the Penrose transform, which is the isomorphism we have up there. But of course, now, in the non-abelian case, these are 3 nonlinear partial differential equations, right? Because of the commutator that we have here. So nonlinear PDEs are hard to solve. So in general, if someone just gave you this problem, you would say it was going to be very hard to construct solutions. But twistor theory provides us with a way to generate all solutions to these equations. Okay, so how does that happen?
You mean all the self-dual?
All the self-dual solutions, yeah. Yeah, sorry, these are the equations we're talking about. Solving them automatically solves the Yang-Mills equations, but of course, not all solutions to the Yang-Mills equations are self-dual.
Okay, may I ask, could we obtain larger class of solutions than that from the twistor theory, or are we just restricting ourselves?
So this is a great question. Let me return to the question at the end of the lecture. If I forget, ask me again. But just because the short answer is no. But somehow that shouldn't stop one. So ask me again at the end if I forget to readdress this. Okay, so the basic result is the following theorem, which is due to Richard Ward from 1977, which is that there's a one-to-one correspondence between, so on the one hand, self-dual Yang-Mills fields on M with gauge group GLNC, and on the other hand, holomorphic vector bundles on twistor space of rank n, which are topologically trivial on restriction to any twistor line. So remember, a twistor line is a holomorphic, linearly embedded Riemann sphere in twistor space that corresponds to a point in complexified spacetime. So just really quick before I say anything else, you might say, well, geez, GLN, don't I usually like to study things like SUN gauge group? And of course, there's versions of this theory for SUN that require a few more technical assumptions. But this captures the essence of the result. So as ever, there may be some kind of, depending on your background, daunting or not daunting mathematical words here. But really, the thing that's running the show is the statement that if you want solutions to the self-duality equations on spacetime, you get them by building some holomorphic vector bundle on twistor space. And what does it mean for a vector bundle to be holomorphic? Well, there are actually many equivalent definitions thanks to the Nylander-Nirenberg theorem. But one way of thinking of what a holomorphic vector bundle is that it's just a vector bundle that's equipped with a partial connection. So something like a d-bar operator. You remember yesterday we wrote down this d-bar operator on twistor space that takes pq forms to pq plus 1 forms. So now you're just going to give some kind of covariant version of that acts on sections of this bundle. And the requirement of holomorphicity is just that that partial connection squares to 0. Okay, so we can be a bit more precise. So I'm going to give let's put it in quotes, a proof of this theorem. It's not really a proof of the theorem in its full generality in ways that I hope I will make clear as we proceed. So how does this go? So first, we're going to do the 2-to-1 implication. So that means we're given a holomorphic vector bundle of rank n on Twistor space, which is topologically trivial in restriction to any Twistor line. Now, the first thing is you might wonder, why do we have this condition here? Well, because this topological triviality condition. So if we want whatever we have on Twistor space to correspond to something local in space-time, like a gauge field, it had better not have any interesting information lurking in it when you restrict it to Twistor lines, right? A Twistor line is a point on space-time. So if this was not topologically trivial over a Twistor line, there's no way you could get a local object on space-time out of it. Okay? So we have E over PT, which is holomorphic. So this implies the existence of an operator, I'll call it big D bar, which takes PQ forms on Twistor space, which are valued in this vector bundle, and sends them to P Q+1 forms on Twistor space, which are also valued in this vector bundle. So locally, that means you can write D bar as just the D bar that we wrote down yesterday, just the usual complex structure on Twistor space, or on CP3 restricted to Twistor space, plus some sort of connection one form where this little a should take values in 0, 1 forms on Twistor space, valued in endomorphisms of this bundle E, and homogeneous of weight 0. So I don't know if you guys remember this yoga for reading these symbols from yesterday, but this is just the omega with the numbers tells you the degree of a differential form and where that differential form points. So this is a 1 form that points in the anti-holomorphic directions of Twistor space. It lives on Twistor space, and it's homogeneous of degree 0. So usually, remember that you had these OKs yesterday? Usually when we have O of 0, we just don't even write the argument. And it's also valued in endomorphisms of the bundle, which is the thing that makes sure that it maps sections of E to sections of E. Okay? So locally, you can think of it the same way that you think of a gauge connection on space-time in terms of some gauge potential. And the holomorphicity.
But why 0? Because we're solving for helicity 1, right?
Indeed. Well, okay. This is a nonlinear version of helicity 1. Set h equal to 1 up there. Yeah. But just more generally, even if you didn't know this theorem, if it was twisted by a non-trivial bundle, it wouldn't be mapping E to E. It would be mapping to E by some twist, which we don't want for the partial connection. But yeah. No, very good. And the holomorphicity condition is just telling us that this partial connection has to square to 0. Okay. So putting it up too high. So the assumption that E restricted to X is topologically trivial combined with the holomorphicity assumption on the partial connection on the vector bundle itself more generally over all of Twistor space implies that generically the restriction of the vector bundle to any Twistor line is in fact holomorphically trivial. Now what does that mean? So that is a fancy word for the following. We can find, if you like, a gauge transformation on this vector bundle restricted to any Twistor line that makes it look flat. So that means that there should exist some h of x, lambda, and lambda bar. So remember, x labels which twistor line I'm on, and then lambda and lambda bar are like the homogeneous coordinates along that twistor line, just if you like by using the incidence relations. So there should exist, let's call it capital H, which maps from E restricted to X into Cn, where n is the rank of the gauge group GLN that we're hoping to recover on spacetime, the rank of this vector bundle E, such that H inverse composed with this partial connection restricted to the twistor line conjugated by H is just equal to the flat partial connection restricted to H. Now, there's this sneaky word that I included here. So the way you should read this statement is that with these assumptions, generically, this H is guaranteed to exist and to have this property. So you can always solve this equation. Now, that's only true generically. So what do we mean by generically? If you were to replace, in this equation, d bar, big D bar, with this kind of local expression in terms of the flat guy plus some potential, it means that you could solve this equation for H as a kind of Born series in little a. Right? That's a formal series. It doesn't converge. So in some sense, you're only guaranteed that this H will exist for A in some open neighborhood of 0. Right? This is the usual existence result in kind of PDE yoga. You have some open neighborhood of existence. So if your partial connection on twistor space is too big, in quotes, let's just pretend that we can agree what that means, then this holomorphic frame, so this is what we'll call this thing, a holomorphic it might not exist. So in fact, one can construct explicit examples where it doesn't exist. But what I want to emphasize is that this theorem is still true, even in cases that fall outside of this genericity assumption. It's just the method of proof I'm showing you doesn't work. So there's some other more general method that I don't want to get burned by touching that works when such a holomorphic frame doesn't exist. But generally, it always exists, and in particular, it will always exist in perturbation theory to all orders, which is kind of good enough for quantum field theory applications. Now, you can show that this is not unique, of course. This h of x, lambda, and lambda bar is only defined up to h going to h multiplied by some little h, where d bar restricted to x of little h, x lambda bar is 0. So that's easy to verify. You just waz this into this equation, and as long as little h obeys this equation is preserved. So our choice of holomorphic frame is not unique. It's unique up to these little h's, which are kind of globally holomorphic on the Riemann sphere. All right? So okay. But in particular, H is matrix valued, but it's otherwise homogeneous of degree 0. Right? So this is some matrix valued function that's homogeneous of degree 0 on the Riemann sphere, and we're saying that it's globally holomorphic. So there's this general statement that if you have a function with no singularities on the Riemann sphere, that function has to be a constant. Right? So that tells us that, in fact, this h of x lambda lambda bar can't depend on lambda and lambda bar at all. It's actually just a function of x. So it only depends on the choice of which sphere you trivialize on, okay, which sphere you're trivializing on. So in other words, this holomorphic frame is defined only up to gauge transformations on space-time. So already we're seeing some feature that we like. Okay. Now, once you've found an H that obeys this condition, so a holomorphic frame, I'll leave it as an exercise, you can show that this holomorphic frame has to be in the kernel of the partial connection, restricted to curves. And now, let's go back over here. Yes, please.
Sorry, yeah. Is there any data in the left action on H? If you have a full D bar, something that's true to a full D bar, so the left action is one that's the preserves derivation. Is there any data in that?
No. And in fact, yeah, because, I mean, the thing that helps you here is that you end up just with this conjugation, which gives you this that then acts on the H. If you came from the left, you'd always get the full D bar acting on the thing you multiplied by.
Yeah, but it's like it's in the kernel of the D bar. Is there any information?
If you're in the kernel of the D bar, then it's a holomorphic frame already.
But it changes the definition of H. Act on the left of H for something holomorphic.
I mean, you can, but it won't preserve the holomorphic frame condition. We're asking for, so I define big H in this way. This is a definition of a holomorphic frame. And then I ask, is that definition unique? And you could say, well, let me do any wild thing that I like to big H and see if I can preserve this condition. And multiplying from the left, you're not going to get anything interesting out of that. Because the condition you'll have to have is that big D bar of x acting on whatever you multiplied from the left by is 0. But that's equivalent to the thing you multiplied from the left by being a holomorphic frame to start with.
Isn't there a redefinition of the holomorphic frame as well?
You'll get the same holomorphic frame up to right multiplication.
Okay, is that the point?
Yeah.
Okay, thank you.
Does it answer your question?
Yes.
Okay, cool. Yeah. So now,
May I ask something?
yeah, please.
Is it simple to construct this holomorphic frame, like to choose the representative of this?
No, it isn't. So somehow this is all entirely implicit.
Okay.
So you can construct it as a Born series essentially.
Okay.
Whether you can resum this series or not is a different question. Like it's a formal series,
Okay.
and that statement requires you choosing a local representative of the partial connection. So now in general this is so. Let's veer off piste here for a second. So generally. What this is an example of, this theorem is an example of, is a classical integrable system. So what we're going to end up showing, the content of this theorem, is that those self-dual Yang-Mills equations are somehow equivalent to this condition, which is an integrability condition for a partial connection on Twistor space. That's the content of the theorem. And generally, in the study of classical integrable systems, what you have is an integrable system translates some PDE problem into some auxiliary kind of linear problem. And that's the auxiliary problem. So you know solutions exist, but it's an existence, not a construction. It's an existence proof, not a constructive proof. In special cases, which hopefully we'll have some time to talk about, you can be extremely explicit about this.
What is going to be spectral parameter in this case?
So the spectral parameter is going to end up being lambda, the coordinate on the Riemann. So the spectral curve is the Riemann sphere.
If we can show that the derivative of A is 0, order of D and H in the equation which defines the holomorphic frame?
You could. I mean, what you call H and what you call
H
H.
just cancel, and I get that the capital B bar is B bar.
No, so I mean, so sorry. One should. This is not just this guy acting on this guy. This is like a gauge transformation, and then the consequence of this holding is that the gauge parameter acted on by the connection is 0.
Okay.
So a more enlightening way to do this, if you like, to convince yourself, is to write out this equation in terms of a local representative, and what you'll get is a condition that's like A is equal to minus something like this, right? And then once you know that, this equation follows. Does it answer your question?
Yes.
Okay. All right. So now we're going to use the fact that if I have any object F, say, that lives on Twistor space, and I restrict it to a Twistor line, X, then that object is annihilated by lambda alpha d alpha alpha dot. So why is that? It's just a consequence of the incidence relations. If something started out life living on Twistor space, and I pull it back to a Twistor line, that just means I impose the incidence relations on its arguments, right? So that f of z restricted to x, this is just f of mu alpha dot equals I x alpha alpha dot lambda alpha, say lambda beta. Right, so all of the x dependence that lives in this object has to come in this form. So that means if I take an x derivative of the object pulled back to the Twistor line, it always comes with a lambda. So then if I contract with another lambda, I always get 0, right? Because I'm contracting something that's symmetric by a skew-symmetric inner product. It's the same argument every time, right? So we use the fact that this, if you like, vector field annihilates any object that you pull back to a Twistor line, that you restrict to a Twistor line, combined with this defining feature of our holomorphic frame, you can show that this implies that just the ordinary complex structure restricted to X acting on the combination H inverse lambda alpha d alpha alpha dot H is equal to 0. Showing this is an exercise that's in the lecture notes that you'll get later today. Okay. But what does this mean? This is telling us that this quantity, H inverse lambda alpha d alpha alpha dot H, is globally holomorphic on the Riemann sphere and homogeneous of weight plus 1. So why? The H's are homogeneous of degree 0, as we argued before. And the only other thing that carries projective scaling is this lambda that we have here. So that means that this whole object is homogeneous of weight 1. The fact that it's annihilated by d bar, this is just the ordinary Cauchy-Riemann equations on the Riemann sphere, tells you that it has to be globally holomorphic. And by a very mild extension of the argument that we used over here, that said if we had a homogeneous function on the Riemann sphere that was globally holomorphic, it had to be constant. If you have a homogeneous of degree 0, if you have an object that's homogeneous of weight plus 1 on the Riemann sphere, or an object that's homogeneous of positive weight on the Riemann sphere that's globally holomorphic, that just means it's a polynomial, a homogeneous polynomial, times whose coefficients are constant on the Riemann sphere. So in other words, that's telling us that H inverse lambda alpha d alpha alpha dot H has to be expressible as lambda alpha A alpha alpha dot of X, where A alpha alpha dot is valued in the Lie algebra of GLNC. Okay, so this is just a consequence of these generic homogeneity arguments. We have something that's globally holomorphic of positive homogeneity. It has to be a homogeneous polynomial on the Riemann sphere. And the coefficients of that polynomial have to be constant on the Riemann sphere, so they can only depend on the only other variable we have in the game, which is x. Okay? So here we are. We've suddenly managed from this holomorphic frame, which we got from the assumption that the bundle on Twistor space was holomorphic and topologically trivial in restriction to lines, we've suddenly constructed something that looks like it could be a gauge potential on spacetime. And sure enough, if you change your holomorphic frame in this way by a little h, you can show that this A changes by a gauge transformation. So lo and behold, we really have constructed a gauge potential on spacetime. So under h goes to h little h of x, A is gauge transformed. On complexified Minkowski space. So we've constructed a GLN gauge connection on spacetime. We haven't yet shown that this gauge connection obeys any equations of motion, though.
Can this capital A be related to this little a?
So under certain conditions, which I've not imposed here, there is a way to express capital A as an integral.
Is it the same?
Is it? No. This little a is something that lives on Twistor space. Mm-hmm. The big A is something that lives on spacetime. So they're not the same, but somehow the information that's contained in them is the same. So in the case, so we'll do an example when I'm done here, which will hopefully clarify a few things. But what you should roughly think of happening here is that little a is like the Twistor representative for the Penrose transform. Remember, the Penrose transform tells us we have some cohomology class on Twistor space, and this gives us a zero rest mass field on spacetime.
Okay, may I ask, is this A directly connected to the cohomology? Like we basically quotient by something, and does this A basically reflect this quotient structure? Or
Yeah, so we need to be a little bit careful here because all of this Penrose transform stuff is linear. This is a nonlinear argument. In the linear case, all of this becomes true. So let me finish the proof, and then we'll work the linearized case explicitly and see exactly what's going on. But roughly speaking, you should think of little a as being a kind of nonlinear version of a Penrose transform representative from which you could recover big A, or at least its field strength. Yeah, so they are sort of, one does represent the other, but there's no sense in which they're equal. They live on different spaces. Okay. So you can show, again, this is a nice exercise. You can show that this relation we have, H inverse lambda alpha D alpha alpha dot H is equal to lambda alpha A alpha alpha dot. This is equivalent to lambda alpha D alpha alpha dot H inverse being equal to 0, where this is the same D alpha alpha dot we wrote down before. It's the connection associated with this A alpha alpha dot. And this is two equations for one unknown. I mean, really, it's two matrix-valued equations for one matrix-valued unknown. So in principle, you could worry that it's an overdetermined system and there are no solutions. But we know that this H exists, right? So this equation has to obey an integrability condition. It has to, there's some Frobenius integrability condition associated with this equation. But we know that solutions exist. This implies the so there has to be a Frobenius integrability condition satisfied by this equation, which is precisely that the commutator of these differential operators has to vanish. But this is precisely equal to lambda alpha, lambda beta, epsilon alpha dot, beta dot, f alpha beta, where this is the anti-self-dual part of this connection on spacetime. This is a symmetric two-spinner, so the fact that it's contracted into two lambdas doesn't give us any conditions on it at all. Lambda is a varying, it's not a fixed number, so it can vary over the whole Riemann sphere. So the only way that this condition can be satisfied is if f alpha beta is equal to 0. So there we are. We've recovered the self-dual Yang-Mills equations from having a holomorphic vector bundle on Twistor space. Okay. Now, again, I want to reiterate that this method of proof is not the most general one. It requires knowing that you have this holomorphic frame in the game. The more general, most robust method of proof involves representation theory and homological algebra. So, but somehow this method is sort of enough for kind of almost all of the modern physical applications of Twistor theory, particularly in the study of scattering amplitudes. Okay, so then the other way around is fairly straightforward. So here we just showed that if you're given a holomorphic vector bundle on Twistor space, obeying the right assumptions, you can get a self-dual Yang-Mills connection. But the other way around is not terribly bad, although again, I'll be very sketchy about it. So suppose we're given an S self-dual GLNC gauge field on M. So we have that its field strength, FAB, is just epsilon alpha beta F twiddle alpha dot beta dot. So for all points in Twistor space, the restriction of the field strength to the corresponding alpha plane in spacetime. Remember, a point in Twistor space corresponds to one of these totally null two planes in complexified Minkowski space. This is just given by lambda alpha A twiddle alpha dot lambda beta say B twiddle beta dot epsilon alpha beta F twiddle alpha dot beta dot. So all you do is you take two basis vectors in an arbitrary pair of basis vectors of this alpha plane, contract it into the field strength. This is 0 for the usual reason that I have two lambdas and they get contracted by an epsilon. So self-dual gauge fields are trivial, if you like, flat on restriction to alpha planes in complexified Minkowski space. And that means that the set of S, say, functions that are valued in Cn on Minkowski space such that they are covariantly constant on any alpha plane, because the gauge connection is trivial on the alpha plane, that means that covariantly constant functions on the alpha plane are just constants, right? Because the gauge connection drops out of this equation. So that means that the space of these constant functions is just Cn. So this defines for us a fiber of a vector bundle on Twistor space. And we repeat this construction for every single point in Twistor space. It gives us a fiber of rank n on every point. The construction's holomorphic because at no point did I have to invoke complex conjugation anywhere. And furthermore, the fact that it's arising from local functions on space-time ensures that E restricted to any Twistor line will be topologically trivial. So dot, dot, dot. I'm brushing some subtleties under the carpet here, of course. You get a holomorphic rank n vector bundle E over PT with E restricted to X topologically trivial. So again, I hesitate to call any of this a proof, but this is at least a pretty coherent sketch of the actual proof of Ward's theorem. So again, let's just take 1 second to reflect on what this is actually telling us. It's telling us that every self-dual Yang-Mills field arises from this Twistor construction. So for any self-dual Yang-Mills field, you get a holomorphic vector bundle in Twistor space obeying some technical assumptions. And furthermore, every holomorphic vector bundle on Twistor space that obeys these technical assumptions gives rise to a self-dual Yang-Mills field on space-time. So we had a question earlier about the kind of implicit nature of this construction. We have this holomorphic frame that's kind of only defined implicitly by this auxiliary condition. And so all of the juice of the construction is hidden in being able to determine this holomorphic frame. And if you've ever heard of something called like the ADHM construction of instantons, this is what this is doing. It's giving you some algorithmic way to construct the holomorphic data that you need to build a self-dual Yang-Mills field. So it can be operationalized, but maybe what I'd like to finish with is just one very simple explicit example, which is when the self-dual Yang-Mills field is actually a self-dual Maxwell field. And so in some sense, we already know how to do this. We have the Penrose transform, but let's see how it works kind of in this language. So of course, because this was first done by people in Oxford sort of in the 1970s, it has some snarky name. It's called the twisted photon. So we're going to consider a self-dual Maxwell field. So in the language of Ward's theorem, which of course I just erased, that corresponds to a holomorphic line bundle on Twistor space. So if we locally write our partial connection on Twistor space in terms of a kind of one-form potential, we now have that this little a is just a 0, 1 form on Twistor space that's homogeneous of weight 0, because there are no endomorphisms, no non-trivial endomorphisms of a line bundle, then the condition that this line bundle be holomorphic is that big D bar squares to 0. But now that's just little d bar of A is equal to 0, right? Because if it was a kind of rank n vector bundle, there would also be some commutator bit of A with A. That's not there anymore. So that just means that little a is a cohomology class on Twistor space, right? So we're already back in the ballpark of the Penrose transform, which we expected to be in. But let's, again, see how you would recover the space-time gauge potential using the language of the proof that we just ran through. So consider our partial connection restricted to a line. This is the thing we used to build this holomorphic trivialization in the proof. So that's just d bar x plus little a restricted to x, where again, what I mean by little a restricted to x is I mean a evaluated using the incidence relations. Right. But because little a is a cohomology class up on Twistor space, it means that little a restricted to x drops down to a cohomology class on CP1 with the same homogeneity. And you can show that this cohomology class only has the 0 element in it. So in particular, all 0, 1 forms on the Riemann sphere, which are homogeneous of weight 0, arise from d bar of some homogeneous function on the Riemann sphere. There's nothing non-trivial in there. It's an exercise in the lecture notes to convince yourself why this is true. Or, if you want to just take the word of the gods, you can prove this using the Riemann-Roch theorem for line bundles. It's a straightforward kind of two-liner. Or, I think a more enlightening way is play around and try and construct something non-trivial in this class using homogeneous coordinates on CP1. You'll soon realize that you can't do it. Okay, so this object has to be, if it's 0 in cohomology, remember that doesn't mean that it's 0, it just means it's d bar of something. So that means that a restricted to x has to be written as d bar of x, d bar on the Riemann sphere x of g, say of x lambda bar, where g is just a smooth function on CP1, homogeneous of weight 0. Okay? So in real money, that's what this means. It just means that when I take A and I restrict it to a Twistor line, I get d bar of some function on the Twistor line. So this means we can solve big D bar restricted to x of h is equal to 0 by taking the holomorphic frame to just be the exponential of this g. And then that in turn implies that this quantity, h inverse lambda alpha d alpha alpha dot h, which we used to construct the self-dual gauge potential on spacetime in the general case, this is now just given by minus lambda alpha d alpha alpha dot g, and that's supposed to give us lambda alpha a alpha alpha dot. So this one upshot of this is that you get now an explicit formula for a alpha alpha dot of x, so the space-time gauge potential in terms of little a on Twistor space. This is the thing Yurik was asking me about earlier. So remember, the way we wrote down the Penrose transform yesterday, it told us that elements of this cohomology class corresponded to zero rest mass fields on spacetime. And that meant what we would get directly from these integral formulae that we were writing down is not the gauge potential, but it's gauge invariant field strength. This actually gives you a way to get the gauge potential directly. And you have to make some choice, which is a gauge choice. So in a light cone gauge, say where, let me pick some constant spinner omicron and omicron twiddle alpha dot. So that's a null 4 vector by our usual SL2 spinner yoga. And I say I want my gauge potential to be in light cone gauge with light front gauge with respect to that null vector. Then you can write down the following integral formula. So there are details in the lecture notes of how you can prove that this is actually correct. Okay, and I think I'll, rather than getting into a whole nother discussion which will take us over lunch and get us hungry, I think I'll stop there for today. Thanks.
So is it easier to find little a than to find the capital A?
I'm not, so do you mean if you hand me a self-dual gauge field on spacetime, is it easy to construct the partial connection on Twistor space?
No, if you want to construct self-dual A, is it easy to find those little a's?
Ah, so okay, so again, in general, you have some kind of implicit problem that you have to solve. And usually, if you're clever, you can guess the right Twistor representative to do the business. But in general, like, so for instance, you could take the kind of first topologically non-trivial example, which would be SU2 Yang-Mills instantons on Minkowski space. So these are topologically non-trivial self-dual gauge fields. And there you have to make some very clever ansatz for how you construct the holomorphic frames on Twistor space. This is something called the Atiyah-Ward ansatz. So it's known how to do it, but you have to have some nice insight for how to satisfy this implicit kind of PDE problem that you've boiled things down to. I should also just say really quickly, we got, I had a question about lax, or about spectral parameters. So I can't remember where that was from, but so if you're an integrable systems person, the lax pair associated to this problem is that precisely this lambda alpha big D alpha alpha dot, and lambda alpha plays the role of the spectral parameter. So anyway, yeah, sorry, I'll stop there.
Now I come back